Now, let us see the free surface of a rotating fluid liquid. So, consider a vessel in which a liquid is confined and this vessel is rotated about its axis omega like this. So, you see this is the free surface of the liquid. So, this liquid is under rotation about this axis and I assume that 0 0 the origin this. So, I am interested in this equation. So, let us consider a point here, this is P. Now, consider a liquid in a vessel which is rotating about the axis shown with angular velocity omega. So, this is the angular velocity omega. We wish to know the free surface. So, what we do? We consider again a fluid particle of mass m on the free surface. So, the net force should be always the net force on the fluid particle should be always normal to the free surface. In other words, there should not be any unbalanced force along tangential direction. So, now let us come to P. What are the forces? In the frame of P itself, the real force is mg and there is a centrifugal force m omega square x. If I assume that this is x, this distance, that is the distance x from this and this is y suppose. So, if I draw a tangent here with the x axis, the tangent makes an angle theta. So, we have now this is theta. So, this becomes 90 minus theta. So, m omega square x cos theta becomes mg cos 90 minus theta. Cancel, omega square x cos theta is equal to g sin theta. So, here you see omega square x by g becomes tan theta. This is very important result. Tan theta is the slope of the tangent to this curve. So, this tan theta is written as dy by dx, that is omega square x by g. So, if I integrate it, then on integration it gives y is equal to omega square x square by 2g plus constant of integration c. Now, y is 0 when x is equal to 0 implies c is equal to 0. Thus, y is equal to omega square x square by 2g is the equation of the free surface. This is a curve, but free surface is a surface. So, the surface generated by this, by rotating this curve is actually y is equal to omega square x square by 2g. So, if you rotate this curve, you get a paraboloidal surface which is the free surface. Now, suppose this is a vessel in which the liquid rotates, and this is the free surface. This is the free surface. The liquid rotates with omega angular velocity, free surface. So, you see, if I want the pressure at this point, this is atmospheric pressure Pa, this point will have Pa plus H rho g. Similarly, another point which is at the same distance from here, another point here, same distance. So, again if I will draw, this will be again a parabola. So, these parabolas, parabolas of equal pressure, that means all the points on these parabola will have the same pressure which are parallel to these parabola. So, all the parabolic paths which are parallel to the free surface are the parabolas of equal pressures. We sometimes use this property to solve certain type of problems. Let us see. Now, let us take an example where I am going to use the idea of the free surface of a rotating liquid. So, we have a circular tube in which we have some liquid. So, this is circular tube which contains a liquid, and this tube is going to be rotated about its diameter. So, this is the diameter, and initially the tube occupies this portion only. So, this is the liquid initially, which is a quadrant of a liquid. So, we have a quadrant of a liquid in a vertical circular tube. Now, the tube is now rotated about its diameter. So, let us rotate this tube about its diameter, that is the vertical diameter, that diameter is vertical. So, now the liquid in the tube then rises to a position where its one free end makes an angle 60 degree with the vertical. That means the liquid goes to this position. So, the liquid suddenly goes this way. So, now in the new position of the liquid is this. Previously the liquid was here, now it is here. So, how much omega is required to do so? So, this position is 60 degree, and so this is 90 and this is 30 degree. So, this is the problem. So, in order to shift this quadrant from here to here, the liquid column from here to here, how much omega is required? This is our situation. What to do so? This is 60, means it will be very near to this position, So, this position, and you see it's 90 means nearly it is like this. So, we have the liquid column at this position. So, now the idea of using the free surface of a rotating liquid is here. So, you can see I can imagine a surface, free surface like this, you can see so now you see here the liquid, this liquid column, this liquid is up to here, the shaded one, and when I rotate it, this is the free end and this is the free end. So, this point and this point must have the same pressure. That means the free surface, these two must lie on a paraboloidal surface whose equation is given by our free surface, that is y is equal to omega square x square by 2g. So, this is the parabola and this is the vertex of that. So, now what we do, let this point be represented by O. If I drop a perpendicular, this is N, and if I drop a perpendicular here M, and this is the center C. So, I wish to know what is the omega required so that the liquid comes to this state where this is making an angle 60 degree with the vertical and this end makes an angle 30 degree with this vertical. So, in order to reach at this configuration, so my point is that in that situation the free surface, that is of the liquid, rotating liquid, must pass through these 2 points. So, for this to happen, let us see what we have to do. Now, this equation is y is equal to omega square x square by 2g. The equation of the free surface, that is y is equal to omega square x square by 2g. This is the equation of the free surface. Now, the free ends of the liquid column must lie on this parabolic path, parabolic curve. So, number 1 point, let us see, this is AB. So, A lies on it. So, A lies on the parabola, free surface. So, let us see A. So, you see, let us see the coordinates of A. So, this is radius A, and this A sin 60 is equal to root 3a by 2, and we have this A as A cos 60, that is A by 2. Again, here this is again A. So, we have this B as A sin 30, that is A by 2, and this will be having A root 3 by 2. So, now let us see, we will put this y. So, y, that means OM. So, y is equal to omega square x square by 2g. This implies y is OM, that is omega square by 2g. What is the value of x for A? That is root 3 a by 2. So, this is equal to root 3 a omega square by 4g. Next, point 2, B lies on the parabola. B also should lie. So, we have y is equal to omega square x square by 2g, implies ON is equal to omega square by 2g x square. So, here I have to do some x square also, that is I have to do this square. So, here it will be again, that is 3a square. So, 3 omega square a square by 2 into 4 into by 8g. So, here again x square, x means a by 2 whole square, that is a square omega square by 4 into 8g. So, 2 square 4, 4 into 2 8g. Now, you see here Mn is this plus this, So, in order to know Mn, so we have now, we have Mn is equal to OM minus ON. So, this is OM and this is ON. So, we want Mn, that is the difference of these two, that is omega square A square by 8g common, 3 minus 1, that is 2. So, omega square 8g, omega square A square by 4g, and this Mn is itself equal to A by 2 plus root 3 A by 2 is equal to omega square by 4g, implies this is A by 2 root 3. So, 1 plus root 3 A by 2 is equal to omega square A square by 4g, A cancel, implies omega is equal to, here 2 cancels, 1 plus root 3, 2 times 1 plus root 3, this is g by this is A and this omega square. So, root over this. So, thus we see that how we have used the concept of the free surface of a liquid to determine the new position of the rotating liquid column.